thank you, Sue, for the intro. Since you're all here, I presume you're all interested in audio at some level, but I have no idea what kind of background everybody has here. So before I start, I just want to see, okay, first off, how many of you are musicians? Do any of you play musical instruments? Okay, good number of you. How many of you, can you all hear me? Without a microphone? Okay, I won't use a microphone then. How many of you have opened up an audio editor and looked at a waveform? Yeah, okay, good. All right. How many of you have written code to generate audio or process audio, like at the sample level? Okay, just a few of you. All right. Okay, so, all right. So what I'm going to be talking about, well, actually, getting ahead of myself. Let me just start with the slides. Okay, so I'm going to talk about some audio DSP basics, really basic stuff. So a few of you who've done some audio processing, you might find it a little bit boring, but some of the rest of you hopefully will find it interesting. And I'm going to provide you all with the source code that I'm going to show here. It's mostly going to be code examples that I'll show. And all in C++. Okay. So a bit about my background, very briefly. I've an electrical engineering degree from Queen's University of Canada, master's in electroacoustic music from Dartmouth. I've worked, most of my recent work has been in iOS, so I have a few apps that I've shipped for various companies. And before that, I've done speech recognition for Apple, video editing software for muvee. I used to do hardware design for Nortel networks. So I've done a whole bunch of stuff. I'm probably older than I look. At least I hope I'm older. So I'm going to show you a bunch of examples of just C++ code, all in standard C++, so you'll be able to run this on whatever platform you want. Basically synthesizing a basic tone programmatically, reading and writing a WAV file, mixing multiple audio files together, changing the play speed of an audio file, some very basic filtering, and also how to apply pan and balance if you've got a stereo file. It's all really simple stuff to do in any audio editing app, but here I'm going to do it at the low level. There's a link down there for downloading the code if you want. It's probably not there yet because I'm uploading via my phone right now. If it doesn't work, I have it all on a thumb drive here. Okay, so without further ado, we'll go straight into some code. Let's see. Okay, so I have basically a, is that all visible? Yes, okay. So I have a very simple just console application with a bunch of examples down here at the bottom for doing the various examples. And I'll start with just creating a tone. So if you've ever looked at a waveform of, in a waveform, if you zoom in enough, you'll see that you have, a waveform that goes up and down. So I'm going to synthesize a waveform here. So, so just briefly, code overview here. I create a buffer for my output, and with a certain number of sample frames, I'll just run a loop, and in the loop, I generate a sine wave at a certain frequency. Sample rate is 44 kilohertz in this case. And so I just fill up the buffer with a sine tone, and I'll write it into a wave file. So I'll just run that. And so it's run it, and let me just go back to the Finder, and there's my tone. Sorry about that. There's no, it works. Yay! I wish there were a volume control on here. Okay. Okay, now if you're any of you who are musicians, you probably know that instrument tones, they're not just sine waves. Typically you have overtones, and the relative levels of the overtones, that is overtones or harmonics, they change the sound quality. So now I'm just going to generate another tone here, but I'm going to add in some harmonics. So I'm going to add second, third, fourth, and fifth harmonics at different amplitudes here. And I run this. And I'll get another tone, which will probably sound about the same because the speakers are distorting so much. But we'll see. I'll turn down the volume this time. Okay. So now you get a slightly different sound. It's more, it's a slightly richer sound because it's got some harmonics in it. Now, if you, obviously those aren't very interesting sounds, but if you actually do real synthesis of interesting sounds, if you get down to the very, very low level, ultimately you're just, often, this is one way it's done, just adding up harmonics to generate interesting sounds, and then applying envelopes on it, time envelopes, to get smooth attack and a smooth decay on the notes. So that just demonstrates generating some audio programmatically and writing it to a WAV file. Next, I'll just okay, so I'm not going to do any more audio synthesis. The rest of the examples are just going to be processing audio in various ways. First example is just really trivial. This is just showing how you can read in an audio file and write it to another audio file. So I'm just going to you probably recognize. Yeah, I should have made it more of a surprise. Anyway, this one I must turn down, otherwise it'll blast your ears out. So, okay. He's back in the charts. Yeah, he's got a #1 hit in the UK right now. Amazing. But 20 or 30 years after he first hit the top of the charts. Good for him. So next I'll just show mixing audio files. Again, apologies to anyone for whom this is just so obvious and basic, but if you've never done audio programming before, some of this stuff is not necessarily obvious. So this next example is just mixing audio files. So here I read in 4 different audio files. It's funny, my mouse doesn't work properly here. So here I read in 4 different audio files, each into its own buffer. And then in a loop here, I add in sample by sample contribution from each of the 4 different parts. So I have bass part, guitar, keyboards, and drum kit. Write it to an output buffer, and then finally write it to an output WAV file. And it'll work better if I run it. So I'll just run that. So it's done. Just show you what the source files sound like, just a couple of them. So there's the bass track, drum kit, and the mix that was generated is this one. So that's basically all there is to audio mixing. In the most basic sense, audio mixing is just adding up the signals. And if you want to, mix things with different gains on them, that's just a multiplication. So if I want to, have the bass be softer and the drums be louder, I just multiply the samples, multiply the sample values by some gain. So now I'll have, I've reduced the gain on the bass and I've increased it on the drum kit. So now we'll hear louder drums and softer bass. So pretty straightforward. And again, after the presentation, you can download all this, or get a copy of all this code so you can play around with this stuff yourself. Okay, next one is a little bit more fun. I'm going to change the playback speed of an audio file. And this is a very, very simple change, playback speed change. Basically, if you have sampled audio and you want to play it back more slowly, you just have to read through the samples more slowly. But since you only have samples at specific points, in order to make it sound good, what you need to do is interpolate between the sample points. So suppose I'm advancing by, 2/3 of a sample, from this point to this point, but I want the value 2/3 of the way through. I just kind of draw a straight line between the two actual values, linearly interpolate to get a new sample value. That's the most common way of doing the interpolation. There are better ways of interpolating, but they're substantially more complicated. So I'm going to do that Rick Astley file again, but I'm going to make him sound a little lower pitched. So I'll play through at say 75% of normal speed. Okay, in the loop here where I'm generating the output samples, I have I have a source position. So this is where I want to grab a sample from the original samples. I take that position and turn it into an integer part and a fractional part. So that's figuring out, okay, if I'm at sample, a sample here, partway between two samples, I want to get this sample value and this sample value, and I want to know how far I am between the two of them. So the integer value is the index of one sample. The fractional part is what percentage of the way I am between those two samples. So that's what's happening in these two lines where I get int pause and frac. Then I get the samples from the source buffer before the previous sample and the next sample, and I do linear interpolation between those two samples and increment the position according to how fast you're playing through it. So I'll just run this. And we're done. We have a output file. So this is Rick Astley played more slowly. Now, you notice that it's not just slower, it's also lower pitched. So his already gravelly voice becomes even more gravelly. And that's what happens if you change playback speed in this very basic way. You've probably, many of you have probably seen applications that allow you to slow down audio without changing the pitch. I have one myself. I've written one called AudioStretch for the iPhone. It's possibly the world's best. I'm not going to demonstrate how to do that because that's actually very, very complicated. Requires some very advanced signal processing, including Fourier transforms. You need to take stuff from what's called the time domain into the frequency domain, play around with phases, then go back to the time domain. It's very, very involved. A lot of black magic involved in it. But just changing the speed like this, it's actually kind of fun. It's equivalent to changing the speed on a tape player, for example, or changing the playback speed on a turntable. Yes. Do any of you know, have any of you seen those big old discs? You know those big black things? Vinyl, yeah, that's it. Yeah, I call them bulky discs, as opposed to the compact ones. Okay, so if you change the speed on a turntable, that's equivalent to doing this very simple speed changing. Okay, next. What else? Okay, so changing speed. Next, I'll just show applying some basic filtering. Again, using Rick Astley. It's good to be consistent because then you get used to what the sound is, right? Okay, so first I'm going to do a low-pass filter. So, okay, I have a class here called a biquad. A biquad filter is a certain kind of filter topology. You can read all about it in the comments. There's a fair bit of funky math involved, but the way I've packaged it up, it's really pretty easy to use. You just
can I just make it in a presentation mode?
Oh. Oh wow. Okay.
iOS experts.
All right. Okay. Great. Nice. Now I can almost read it without my glasses. No, not really. I've been programming for too many years. Okay, so biquad filter, I just initialize it, specify the sample rate, and here I initialize it as a low-pass filter, and I'll have a cutoff frequency of 400 hertz. Now what a low-pass filter does is it passes any frequencies that are below the cutoff. So it means in this case, anything below 400 hertz gets through, anything above 400 hertz is gone, more or less. And what that will give you is a really muffled sound. Okay. So here's Rick Astley filtered. Okay. So a muffled version of Rick Astley. And conversely, if I do a high-pass filter, that means you'll only have, in this case, only have frequencies above 1,000 hertz. So you basically lose all the bass, and it'll sound really, really tinny. Sort of like what you get from your iPhone speaker. Right? Okay. Now some of you might notice, if you're musically inclined, that even though there are no frequencies above 1,000 hertz, you're still hearing notes that are below 1,000 hertz. The reason for that is that the notes as instrument tones, as I was explaining in the very first example, they have multiple harmonics, and even if the fundamental frequency, the actual component at the note itself is missing, your ear can still figure out the notes based on the harmonics. That's one of the magical things that the ear does. Sorry?
Is this component at this frequency completely missing, or is it just decreased?
It's, in this case, well, here the cutoff frequency is at 1 kilohertz and it's rolling off.
Is it whether like minus 20 dB?
It's,
or something like that?
it's, it's a bichord, minus 6 dB per octave? Yeah, minus 6 dB per octave. So, by the time you're down at middle C, which is like 260 hertz, you're down by 12 dB, which is, it's quite a lot. Even if you had a steeper cutoff, you would still be able to hear the notes. Like you could have a piano playing in middle C. You could eliminate everything below, say, 500 hertz, and you'd still hear it perfectly clearly as a middle C. And in fact, with telephones, telephones pass almost nothing above 300 hertz or so, 400 hertz. But the pitch of the human voice, male voice, averages around 100 hertz. So the reason you can still hear it and hear it at the correct pitch is because of all the harmonics. And in fact, with the voice, all the different vowel sounds, they're just different different harmonics. If I'm doing that kind of mouth movement, I'm just shaping the harmonics. That was kind of embarrassing. Sorry, go ahead. Yes.
Is it one of these filters that's used to get rid of background noise? And when you're trying to filter out background noise?
You can use that. A simple filter like this is it's good for eliminating some kinds of background noise. Like if you had, say, hum at 60 hertz or 50 hertz or something like that. You want to get rid of that.
That's what they do in like server, for canceling server noise.
Yeah.
That's more or less what they do in server
Yeah.
cases.
Yeah. But it's not great. It'll tend to well, most noise tends to be across many frequencies. So there are some much more sophisticated ways of eliminating noise, but on a basic mixer, this is more or less the kind of filter you would have.
Sure.
Basically, high pass, low pass, band pass filters. This biquad class, you can initialize it in to do many different kinds of filters. I've just shown high pass and low pass here, but there's also band pass and notch filters. Yeah.
Is that how lossy compression works? Like they cut up and then let a brain reconstruct?
No, lossy compression is quite a different thing. With lossy compression, what they do is they basically analyze the sound in frames, in short intervals of maybe 20 milliseconds, 50 milliseconds, something like that. Transform it into the frequency domain, and then figure out what bits of the frequencies, which frequencies you actually won't be able to hear because they're masked by other frequencies. Masking is like if you have one very loud tone at a particular frequency, like a very loud tone at 440 hertz, and then there's another one that's very quite soft, say at 500 hertz. You probably won't be able to hear it at all. So you can kind of throw away that information, and that's how you get compression. There are other psychoacoustic properties that are used, but the main idea is just masking the fact that there are sounds that you just don't hear, so you can throw them out. Okay, next I'll just do one final example here. Again, really trivial for people who've done this kind of thing before, but you know, if you've never seen it, it might be kind of interesting. I'm going to take a stereo audio file this time. Everything I've done so far has been in mono. This time around I'm going to use a stereo audio file. So when I read it in, I actually get 2 channels. Num channels is 2 here. And I'm going to read through the audio frames, and I end up with, I actually have 2 buffers in this case, one for the left channel, one for the right channel. And I'm going to apply balance function to it. And what this does is just, it changes the gain on the 2 channels. So if you pan something, say, fully to the left, what that means is keep the left channel at full volume, but completely cut out the right channel. Similarly, if you pan it fully to the right, you keep the right channel and turn off everything on the left. So with the balance at 0, that means in the center in this case, we'll get the original sound. Is the audio in stereo here?
Find out.
I think it's playing in mono.
Yeah,
Okay, well, this is one reason why I did everything in mono up to now, because I thought this might happen. But you can take my word for it. In Stairway to Heaven, at that point, the guitar is fully on the left. It's fully on the left, and the recorders are fully on the right. So if I just do a, if I adjust the balance so that it's more to the right, I won't do it fully to the right, but most of the way to the right, I'll have pretty much all recorder and very little guitar. I think it was the other way around. Yeah. So now, okay. So now let me try to switch it fully the other way. So I'll go full left. Could be a bug in my code too. I wrote this about an hour ago.
It's really hard to hear. The loudspeakers are.
Yeah.
I think they're mono.
And even if they're mono, you'll hear the channel.
Yeah.
Yeah, you should hear. You did hear the 0.8. It's kind of
Yeah.
soft. Yeah. It's much louder, right?
Okay.
Right?
Okay, that's all guitar.
You can just hear the amplitude.
Okay. So let me do it fully the other way. So we.
Okay,
Whoops.
so
Whoops.
I still have my Led Zeppelin history, right?
Yeah. If you're trying to transcribe stuff, it's sometimes very useful to be able to just set the balance on things. Okay, so now we have full right, which, according to our Led Zepp aficionado here, it should be all recorders. Yeah. It's just very soft. Unusually soft. I think the audio is actually only picking it, almost only picking up one channel here. Okay, so there you go. That's pretty much it. Let me go back to the presentation here. How do I bring up slideshow? So there you go. There's the download link for all the code in these examples. Let me just check whether that's actually there, though. Hold on. Huh? Never mind. If you want the code, just just ask me and I can pass you the thumb drive. Any questions? No? All right. Well, if there's anything you want to ask me, feel free to ask me afterwards. There's a lot of stuff I know beyond this. I just kept it very, very basic for starters.
Do you have an interesting example of on an iOS app something you had to do to manipulate sound? I mean, I know there's your own stretch app, but like usually I always think of it as like playing this clip here, play this clip there. But have you actually seen people changing the sound on the fly?
Well, I mean, that's what my AudioStretch app does, a lot of that. Also, if you look at the BandLab app, BandLab, it's another Singapore company. I wrote the audio engine for that app, and that allows you to record multiple tracks and play them, edit them in various ways. For them, I'm also writing a synth, a sample-based synth, which incorporates, pitch shifting and envelopes, all kinds of stuff in there. Yeah. Doing reverb, I'm writing reverb for them, and yeah.
You have an app on the App Store. AudioStretch.
Yes, AudioStretch. I
use it to
I have
fasten
several.
the podcast to
Yeah.
AudioStretch. Email.
Several different apps. So AudioStretch, Smart Scales. Smart Scales is an app for if you're studying for ABRSM music exams, and you want to practice scales and arpeggios, and you want some interesting background music. That's what Smart Scales does. BandLab is a cloud-based audio production tool, collaborative cloud-based audio production. So you could, say, record a guitar part and then share it with people, and then they could add a drum track, add a vocal track. It's very cool, Singapore-based company. This app I released a couple of days ago. It's for another company I'm working for. These are all for different companies, actually. So this one is a vocal transformation app, so you can record selfie videos and then change the voice. So if you want to make yourself sound like a giant, or you feel like changing your voice into a woman's voice for some reason, you can do it.
Is that available on Google Play?
No, sorry. It's Apple only. Yeah.
Master race.
Yeah. Okay. So, sorry. Yeah.
A little bit of an off-topic question, but in your perspective, what kind of education should an audio engineer pursue?
Well, it depends what you mean by an audio engineer. The term can mean different things. If you mean like an audio engineer as in someone who records and mixes records, then my guess is that you should take one of these MusicTech programs in junior college and get as much studio experience as you can. As far as I can tell, people who do well in that business, they mostly learn on the job. If you want to do audio signal processing, like low-level code, then an engineering degree with lots and lots of math. That's what we need to do. But they're very, very different disciplines. People who do audio engineering in studios, they generally have no idea how the tools really work at the mathematical level. And they shouldn't, they don't need to.
And with virtual reality becoming more mainstream, how's that impacting audio? Or they're using a lot of these devices in like the Google cardboard type stuff?
Yeah. It's funny you should ask that. I was recently contacted by Microsoft. They were interested in, they're doing their HoloLens stuff. And now audio is becoming a part of that, so they want to do 3D audio, right? Because if people are looking at a scene in 3 dimensions and their audio sources, the audio sources, if the things in the world are moving around, of course the audio needs to move around as well. People have been doing that for many, many years. You know, spatial audio is not anything new. You know, it's been used in games for decades. It's just now it can be done much, much better because there's a lot of processing.
Fast enough?
Sorry?
Tracking fast enough to recreate like if you really want spatial audio experiences, is it technically easy at the moment or possible or not at all? Like if you imagine just relying only on audio and having like a virtual world to navigate.
Well, the most straightforward way to do it is using something called head-related transfer functions, HRTFs. So basically, you figure out how a sound coming from a certain direction gets transformed on its way to the 2 ears. Okay, so there's a time delay, there's a bit of filtering. If you have these HRTFs for every possible position, elevation, and direction around you, then you can take any source and process it through the HRTFs and interpolate between them. So you can basically make the sound like it's coming from anywhere. If you want to do it really well, you should also take into account the speed of sound as well, so that a sound that's coming towards you is higher in pitch, and as it's moving away, it drops in pitch. Doppler effect, exactly. But you know, with enough memory and CPU, you can do all those things. Go ahead.
I'm just trying, now that you're working a lot in mobile, do you find yourself having to spend much effort compensating for hardware that sucks? Like speakers and microphones rather than CPUs?
This is why I work on iOS. I mean,
Android's not really designed for real-time audio processing.
Android is getting much, much better. Much better, but historically it's been terrible. Windows has been pretty bad, but again, it's gotten much, much better. iOS is still, as far as I know, the best. And so if you want to do something where you have, where real-time response is important, like if you touch the screen and you hear something right away, iOS seems to be the only option right now. It's the only one that's good enough, say, for a professional musician to do that. But the others are catching up fast.
What's the reason for that? Can you elaborate why?
It has to do. It's not really hardware. It's not a hardware issue. It's more an operating system issue. Basically, to do audio, you need to be able to. You need to have you need to be able to change processes extremely fast. You need to be able to switch to your audio process extremely fast, then go back to your UI thread. Okay, but your UI code should never take priority over the audio thread. And in Apple's OS, both on Mac and on iOS, they've managed to make that processing very fast and efficient. So you can use very, very short buffers when you're generating audio on the fly. Okay.
So I was wondering if there's any research that is if you find that it looks like everything is done. It's the thing. What is the real challenge now? Do you know any? Like we know do speech processing, speech recognition.
Yeah, there's still things that are very hard to do. Just one example of a problem that's still pretty hard to do is automatic transcription. Like you have a recording of someone playing the piano and you want to find all the notes. Right? it's really easy to do badly. It's damn near impossible to do it perfectly. And once you get, a really complicated mix of instruments, it can't be done yet. The sort of recognition rate you see in the published literature, even just for, say, solo piano, if they do 80%, it's fantastic, But from the point of view of the musician, if you get 20% of the notes wrong, that's awful. So that's really hard. Source separation, that's another big one. Suppose you have several people speaking at the same time, and you want to be able to isolate those. That's really hard to do. So there's still plenty of open problems in audio signal processing. Anyway, you can ask me lots of questions later. We should probably let Chin speak.
Thanks, Gerry.
Thank you.